a map of the Earth, and we have here Quebec, Labrador, etc. And there's a line that we draw straight from New York to London, and there's a curved line. Planes, when they fly from New York to London, follow the curved line, not the straight line. The reason they do that is because it's actually the shortest way to get there. Presumably, we would imagine that this black line is the straightest and shortest, but it's not. The white line is the straightest and shortest. The reason for that is simply because map here is a distortion of the reality, right? We can draw a different kind of map, which represents the fact that it's a spherical surface. And then this white line, which was curved, becomes straight, and the black line, which was straight, becomes curved. Okay? And then we'll see that the shortest and straightest path is what looks curved over here is actually straight. Just that we're misrepresenting the situation. Really, it's on this. Okay? So if you draw this as a flat surface, well, you're going to get a distortion. Now what we're going to do is we're going to do something kind of radical. And we're going to say the following. We're going to look at this and say, what I'm going to do is I'm going to distort, I'm going to curve this surface in such a way that the curvature of the surface is going to take up the curvature of this line. So the line will get straightened out. And then the straight line will get curved. Because I'm curving this two-dimensional surface, I'm going to curve it. And by curving it, I'm going to straighten out the line in it. So the curvature of the surface is going to take up the curvature that was in the line. And that's exactly what we do in gravity. We're going to do something outrageous, right, which works, and therefore we like it. And we're going to say this curved world line, which is clearly curved overall, we're going to say, well, it's a curved line in space plus time. We're going to curve space plus time. We're going to bend it, so to speak. We're going to warp it in such a way that the curved world line will turn out actually to be straight, or the straightest possible that could be defined. In the same way as on the globe, the straightest possible line looks curved when you think that you're looking at a flat surface, and only when you realize you're looking at a curved surface do you realize that it's the straightest, shortest possible way. So too, this world line that we draw as a curved world line, it's only curved because we're mistakenly assuming that space plus time is flat, is ordinary. It's not. Space plus time is warped. And it's warped in a very specific way. And that way is that if you indicate the right way, if you were able to do it on a diagram, you would see that this line that you drew as curved becomes straight. As a result, we'll say that space plus time is curved. What do we mean by space plus time is curved? And it's very important to understand that it's only an analogy. You have to be very careful with that term. We mean that we want to warp the space plus time in such a way that what looks like a curved line in space plus time actually turns out to be the straightest. Now, how is it different than this? It's different in two very fundamental ways. When we looked at the globe, what we were looking at is a two-dimensional surface, two space dimensions. Whereas in the world line, what are we looking at? One space dimension, one time dimension. It's not at all the same thing to talk about a warped two-dimensional space where one is time and one is space, as to talk about a warped two-dimensional space where they're both space. Okay. Another difference is that the globe that we're talking about, the surface of the globe, is not a two-dimensional space. It's a surface in a three-dimensional space, an ordinary space. It's just a surface. It's not a two-dimensional space. Right? It has thickness, whatever. It's part of a three-dimensional space. It's very important to realize that when we're talking about space plus time, we are not talking about a surface in a higher dimensional space. We are talking about this two-dimensional space, space plus time. And in fact, we can add on the 3 dimensions of space and make it 3 dimensions of space plus 1 dimension of time. And this whole 4-dimensional space that we'll call space plus time, of which 3 dimensions are space, 1 is time, is warped. It's not a warped surface in some higher dimensional space. That's totally wrong. It's simply the way that time is wired onto 3 dimensions of space is non-trivial. We cannot a priori decide how it's supposed to be. And we can determine experimentally, so to speak, how it is by doing all these little experiments with dropping things and so just little tiny trivial experiments. It's incredible that by doing that we find what the geometry of space-time is. Now, to jump into general relativity, what we would say is, okay, we have this interesting property where the straightest possible lines seem to be curved. We understand that we took too naive a view of what space plus time is. So let's say that space plus time is warped relative to our usual conception, and the straightest possible lines, when represented in this wrong frame, turn out to be curved. But if you would draw them correctly, they would be straight. In other words, space plus time is curved. The free fall world line is straight. If you want, you can think of our graph with space plus time and the curved world line for gravitational free fall. And by warping the axes in the right way, you're straightening out this line. So you get a straight line in a warped space-time. If you look at that diagram the wrong way, like this, you get a curved line. Okay? And that's basically Einstein's theory. Space-time, in his theory of space-time, that's this naive space plus time, space-time is warped. The type of warping that it has is the type that we can call curvature. We're going to see more explicitly and more precisely later on why curvature. But at this level, why would I say that it's the type of warping that we can call curvature? Because it uncurves this line to make it straight. So in this kind of warped space-time, what was curved is now straight, and what's straight becomes curved. Okay, so because of that, we'll call the nature of the warping of space, and we'll call it curvature. And again, we'll see that better later. So what looks like a straight line on the map is actually a non-straight line when you look on the globe. And what looks like a curved line on the flat map, like going up to Labrador and then going to London, is actually the straightest possible line on the sphere. Now, it's the straightest line on a sphere. It's not the straightest line on a flat piece of paper. Okay? On this flat piece of paper, which is a map, the straightest line is the straightest line. But it's only a representation of the reality, which is a globe. So it's not really the straightest line. It's the straightest line only if that flat map represented the true reality. So we're used to drawing axes in flat space on a flat piece of paper, and we're expecting that the straightest line will look like this. But it's just not so. We're representing a space plus time which has warping of the type that's called curvature, and therefore the straightest possible line will in fact look like this, right? A free fall world line.